Sir, we are live now. Please start.
Okay, thank you. So, hello and welcome everyone. My name is Kumar Saurabh. I am senior data scientist working in IBM GTS labs. And today I'll be talking about some of the use cases that I have been working on and some of my colleagues have been working on. Some of the use cases related to IT operations. So GTS actually stands for Global Technology Services. It's a vertical within IBM. And within GTS, we mostly deal with data coming from IT infrastructure, right? So what I mean by IT infrastructure. So IT infrastructure, it's basically, devices like it could be virtual machines running on a data center or on the cloud. It could be network devices like routers and switches. It could be, laptops, edge devices, etc. So all these things comprises of IT infrastructure, right? And the kind of data that we get from this is infrastructure. So if I have to give you a few examples, so let's say if you're talking about a virtual machine running in the cloud, so from the virtual machine we can measure, how the RAM is changing with respect to time, right? Or how the CPU utilization is changing with respect to time. How the disk usage is changing with respect to time, right? So there could be some time series signals. Then there could be server logs, right? It could be text data coming from different servers. It could be tickets data. For example, when we face any problems, we raise tickets with the IT help desk, right? So data related to such help desk tickets, right? So these are the kind of data that comes from the IT infrastructure, and we work with such data to enable some of the use cases, mainly to streamline some of the IT operations and make them more efficient. So I'll give you some examples, then it will be more clear, like what I mean by IT operations and what are the use cases we are working on. So this slide shows few examples. So maybe if I have to pick one, let's say we can talk about outage avoidance using real-time analytics. Right. So what is meant by outage avoidance? So again, let's say we can start with an example. So let's say I'm a cloud service provider, and as a cloud service provider, I might be providing infrastructure as a service or a platform as a service, kind of services to my customers. And suppose, say one of the banks is my customer, and they have carved out a lot of virtual machines in the cloud, and that bank is running a lot of applications on those virtual machines, right? Now, the bank's goal would be like those applications should be running all the time. There shouldn't be any unplanned outage in those applications. For example, if it's a net banking application, so it won't be good for the bank or its customers if the net banking application goes down in an unplanned way, right? So traditionally, how such things are handled is if say some application goes down, so then the bank would contact me and they would ask like, hey, what's going on? Why my application is down? And I, as a cloud service provider, then I would talk to my IT help desk team and ask them to look into it, and they would start gathering a lot of data around it and then see like how to resolve it and eventually be able to resolve it. But all this while the application would be down, right? The net banking example that we're talking about, so that application would be down, a lot of banks customers would have suffered, and it's not good for the bank and it's not good for me as well, right? Because we would have lost a lot of time after the bank has reached me complaining about this problem, and then I would have taken a lot of time to fix this problem, right? So that's not a good situation to be in. So then the question arises, using AI or data science techniques, how I can avoid such situation and be able to identify such outages or anomalies that might happen in the network or in the IT infrastructure even before the bank or who is my customer, even before the bank comes and complains to me. If I'm able to identify by measuring some of the time series signals from the IT infrastructure or some of the server logs from the IT infrastructure and identify that some anomaly is going to happen, and in an automated fashion, a ticket is generated and a person is assigned and fixes, and the IT help desk is able to fix everything much before the bank notices or sees any sort of outage. So that's a win-win situation for both, right, the cloud provider as well as the customers who are using these cloud solutions. So that's an example where mostly anomaly detection kind of techniques are used, right, to find if there are any anomalies or something unusual that is happening in my IT infrastructure, and gather relevant data and be able to fix it before someone comes, detects and complains to me. So that's one use case. Then another maybe I could highlight is about data center consolidation and cloud migration analytics, right? So what I mean by cloud migration. So suppose again, if you're taking example of a large enterprise and it may have like a lot of applications running on an on-premise data center, and they might want to uh, move these applications to cloud-based infrastructure, maybe due to the cost reasons or whatever, right? Now, this kind of migration projects, the main challenge that comes is like, how do we migrate? Usually it's done in phases, right? So the IT team has to identify like what are the applications that are running currently in the data center, and what are the servers and how these servers are talking to each other, right? And once that has been identified, then they send out some notifications to the users of those applications that, hey, these are the 20 applications that will be moved next weekend. And usually it happens in phases, right? This migration happens in phases. So they might identify certain applications and the corresponding set of servers to migrate in one weekend, and then another set of say 20 applications and 50 servers to be moved in another weekend, and so on. And such tasks are completed over a period of time in different phases. Now, the key challenge that comes here is identification of what are the applications that are running, how they are interrelated, what are the servers that are there on which these applications are running, and how they are talking to each other. So first, these has to be identified, and only then the phases can be planned, like the different phases of the migration project can be planned, like in how phase-wise manner I can shift pieces of the part of the infrastructure to the cloud. So in this use case, graph-based methods, come handy here, like graph analytics methods, especially related to community detection. So with such methods related to community detection, we can find like what are the clusters of small clusters of servers, network devices that are related to a set of applications, but isolated from another set of applications, right? So we can identify what are the small communities or clusters within the thousands of servers that the enterprise may have. And once that identification is done, then they can be migrated, and all the phases can be planned, that how to do that migration, right? So that's another example. Then one more example, if I want to talk about, that could be related to say backup and recovery solutions. So for example, IBM has a product called IBM Spectrum Protect, right, which takes care of backup and recovery solutions for large enterprises. So on top of this solution, what we are also doing is adding a data science layer, which can help us to manage this daily or weekly kind of backup in a much smoother way, right? So what I mean by that, so for example, let's say again, if we talk about an enterprise setting, and within that enterprise again there would be a lot of employees using laptops, and there could be applications running on servers, there would be database instances and stuff like that. And then all of these data coming from all of these IT assets has to be backed up somewhere, either on some tapes in a tape library, or it can be backed up in the cloud or disk kind of media, right? So an AI use case here would be like, if I can analyze every day like how much data is being backed up, is there any trend or seasonality in the amount of data that is backed up. And using a time series kind of analysis, if I'm able to forecast, let's say for next 2 to 3 months, how do I see the amount of data backup? How is it growing with time? And using that kind of forecast, I can ensure that there are enough tapes in the tape library to make sure that my backup goes on smoothly in the near future. Right. So that could be one use case in backup and recovery. And another use case would be, monitoring the backup server health itself. So a backup server is responsible for, tracking all the other IT assets like that, for which data is being backed up, or what we call them as protected assets. Right. So if a backup server is responsible for, taking care of so many other protected assets, so the backup server health itself becomes of paramount importance. And by collecting some data from the backup server itself, again, like RAM, CPU usage, and the server logs from that server, we can ensure that no anomaly is going to happen, and the backup server is in good health, and so that the backups can go on in a smooth manner. Right. Then again, if I talk about, say, another example, data could be related to tickets. So for example, when we face a problem, right, we call the help desk, and let's say if printer is not working or facing some issues with the laptops, so we call the help desk and raise tickets, and they start looking into it. Or there could be tickets generated in an automated way also from some systems, like from some virtual machines. Something is going on, some issue is going on, so tickets can be raised in automated way as well, not just always generated by humans. And usually the ticket volume is everyday volume for a large enterprise. It can go into hundreds or thousands, right? So with such kind of tickets data, one use case can be, if we're able to forecast the ticket volume, like every day, like how many tickets are getting generated, then the help desk can plan their operations better. And another way is just looking at the ticket. If a machine learning algorithm can classify it into, a simple classification algorithm, if it can classify it into proper categories, then it can be routed to the right person who can quickly look into it, and thereby saving some time, the amount of time that is typically used to from the time ticket is created till it's resolved. So that also can be saved with this kind of example over here. Right. So these are some of the use cases, that we typically deal with in IT operations, and I gave you some idea of what kind of data, we get to see when you're working with IT infrastructure, devices that are part of IT infrastructure. Right. So this is at a pretty high level, and what I also plan to do today is talk about one of the use cases that I worked on with some of my colleagues in much more detail. So I'll share a little bit of technical details, and try to describe what was that use case, and how that problem was solved using some of the machine learning algorithms. And that use case is related to mainframe batch jobs. So, so you might have heard about mainframes, right? Mainframes have been into existence for more than 50 years from now. And it's like really large machines built for security and reliability, right? So when you want, your system to have zero downtime, so that is when, you go for a mainframe. And these things, like, it has been around for 50 years, but they are still going strong. Most of the Fortune 500 companies, they still use mainframes for their critical business applications. Especially if I talk about airline companies, for example, or banks, or retailers, insurance companies. So such companies which deal in which deal with millions of transactions every day, right? For example, credit card company, right? There would be millions of transactions every day across the world. Or let's say if an airline, right? So if it's so not in COVID times, but if you talk about pre-COVID, right, or once this COVID situation improves, so these airline companies also, like, they could be seeing millions of transactions happening, within a day. So for these kind of transactions, mainframe comes in very handy. It's like it's very good in uh, processing several transactions in parallel. So, and there are two types of transactions. One is real time and one is called batch transactions. So an example for real time transaction would be, let's say I swipe a credit card. I go to a shop and I swipe my credit card. And the transaction needs to be immediately approved, right? So it will be connected in the backend to the mainframe, and from there the approval will come, and then the transaction is approved and payment is made. So that's a real-time transaction. Or for example, when I'm trying to take some cash out of the ATM, right? So such transactions have to be processed immediately whenever it's happening. Another example of real-time could be, let's say when I'm traveling in an airline. So if you notice, like when you're trying to get into the airline, so they scan your boarding pass and then let you in, right? So that is an example of real-time transaction where the transactions have to be approved immediately. So in contrast to real-time transaction, another types of transactions are batch transactions, or what we also refer as batch jobs. So these are nothing but programs probably written in COBOL or C or Java, and they are scheduled to run at some time. So they are not happening like immediately. They don't have to happen immediately when you are doing some transaction. You can schedule them to run at a particular time. For example, I have a program written in COBOL, and I want it to run, let's say 8 p.m. tonight. So I'll schedule it on a mainframe, and when the time comes, it will start running and generate its output, right? So such programs which are scheduled to run at particular time, so those fall into batch jobs. Those are being referred to as batch jobs category. And by the way, if you want to have more information about mainframes, then there is a course in Coursera that is available. So you can look out for this if you're really interested to learn more about it. Right. So this particular use case that I want to talk about in a little more detail, that was related to batch jobs. So for one particular customer, if I talk about, so there were hundreds, more than 100,000 actually, more than 1 lakh, so more than 100,000 batch jobs scheduled to run every day on a mainframe. So that's a quite large number, right? And these jobs like run on every day of the week, or some jobs can be scheduled to run only on weekdays and not on weekends, or there could be some batch jobs scheduled to run whenever they need it. So maybe it's scheduled to run on a Monday and again on a Thursday, but not like every day. So there was a lot of variety of data, more than 100,000 jobs, and each is scheduled to run at their given time. And what happens is with batch jobs, if I give an example of a batch job, so for example, let's say the salary credits, right? So if you're working in a company, usually the salary comes at end of the month, right? So such transactions can be done using batch jobs, right? For example, a program can be scheduled to run by end of the month, which is responsible for salary credits, right? And there could be many other applications. So one another example of batch job could be something called LCR computation. So liquidity control ratio, LCR stands for liquidity control ratio. And it's a regulatory requirement, by the government that given bank has to maintain a certain amount or a certain amount of liquidity in their system, so that they are at a particular liquidity control ratio, and it's a regulatory thing to do. So everyone has to do that. So now this is such critical business processes are supported by batch jobs. And what happens is, let's say, if you might think, what is the big deal? Suppose if a batch job was scheduled to run at 8 and, it didn't start, or probably it started to run and it didn't finish within time. And right, it's got stuck or hung. So what is the big deal? Right. So in such examples, let's say salary credits or LCR computations. So and there could be many other business critical applications like these, where there are like SLAs that this particular transaction or program has to finish by a certain time. And if it doesn't happen, then a lot of business critical applications start getting affected, and people start seeing delays in some of their business processes, right? So 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 after scheduling these thousands of batch jobs, they're not like left alone. There are an army of people monitoring these critical processes that to make sure that are they starting to run whenever they are scheduled to run, are they starting at the correct time or not. And if a job has certain SLA, so is it completing within the time or not, right? So there is a team called a team, we can call them like IT operations people, who are always monitoring whether these jobs are running smoothly or not. And if something is going beyond time, let's say a job was supposed to finish by 10 p.m. and it hasn't, right? So then someone from the IT operations team has to go and look into it and see why it's taking long and do some corrective action to make sure it completes. So either kill the job or restart it, or increase the priority of that job and decrease the priority of some other job, so that that particular job gets more importance, gets more CPU, and it's able to do its task faster and finish within the SLAs. So these are some of the tasks that IT operations teams do in a mainframe context, right? To make sure that all these thousands of batch jobs, scheduled jobs that are running on the mainframe, they're able to finish within the expected time, so that none of the critical business processes are affected. So our goal was like, how do we help these IT operations team who are currently manning these mainframes and monitoring it all the time. And sometimes you will see them in a firefighting mode, right? If some critical application is not finishing, so it really gets escalated if it's affecting some of the critical business process. So how can we help them using some AI kind of solution to manage this process in a better way? So one idea what we did was, let's say if we can forecast, so if I can tell in advance, for each of the jobs. So there are 100,000 jobs. So that is something we want to keep in mind. And for each of the job, if I can tell in advance that, let's say if a job is supposed to run on next Monday, 10 a.m., then using some data science models, if I can tell that when it runs on coming Monday, it's expected to take 2 hours. Or let's say another job, when it's going to run on next Tuesday, it's expected to take 1 hour. So just giving some examples here. So if we can make such forecasts in advance for, let's say, next 1 or 2 weeks, and give those forecasts to the IT operations team, so then they will have some idea, that how long a given scheduled job is supposed to run. And if it's exceeding beyond that time, then they know that yeah, something might be going wrong and they need to take some action about it, right? So this particular problem we dealt with it as a time series forecasting problem. So let me show you some examples of first like what kind of data that we had. So here, if you see my screen, so here I have plotted data for 3 different jobs. So if we start with this leftmost chart over here, right? So this is for one particular job, right? And the data has been plotted for 3 months over here. On the x-axis, it's day of the month, and on the y-axis, it's duration. So it's the elapsed time, basically. On the y-axis, it's elapsed time, the time for which the program ran, and the units here are in seconds on the y-axis, and x-axis are the days. So for example, here if you see on 2nd of December here, this particular job that we are talking about took maybe around more than 2.5 hours, right, to complete. And then you also see here that there are several days. What you observed is the same program, when it runs on few other days, right, or and mostly later part of the month, it finishes within 1 or 2 seconds. So you're not able to see the plot here because of the scale, like the scale of the data is really huge. So you're not able to see any dot here if it's finishing within 1 or 2 seconds, but we verified it manually, like whenever it runs on this part of the month, so it's finishing within 1 or 2 seconds. But during the earlier part of the month, it's taking like 2 to 3 hours, right? And then in between there could be some weekends or holidays where again it's kind of finishing within few seconds. So this particular job was scheduled to run every day, and there was some pattern to it, right? So there is huge variation, you can see, right? So some days it's taking like 2 to 3 hours, and then some days it's finishing within few seconds. So here in this example again, if I give a forecast, like next day when it's going to run, so is it expected to take 2 to 3 hours, or is it expected to finish within 2 to 3 seconds, right? So if I give that kind of forecast to the IT operations team, so they will have some baseline to compare with, right? So they will have, okay, how much time it's expected to take, and when the day has arrived and the job is really running, so they can compare like how much time it's actually taking. And based on that, they can see that is the program running smoothly or something wrong has happened, they need to do something about it. So this is data for one job. This is, this is much simpler data, looks more like a uniform distribution, right? So in this, almost throughout the month, every day, this job is taking close to somewhere between 2000 to 3000 seconds with few spikes here and there. And then another example would be, if you try to visually look at it here. So here you would see like during the first half of the month, this particular job is taking close to 2000 seconds. And on the second half of the month, it's running in close to 1000 seconds, right? So these are some of the examples. So there were like many more. As I said, there were more than 100,000 jobs. But these are some of the examples that I picked to show you that how much variation was there in the data. So for each scheduled job, we had like the historical data that was available to us. Okay, and using that historical data, our goal was to, as accurately as we can, be able to forecast it for the next 1 or 2 weeks and share that forecast with the IT operations team, so that it will help them in monitoring these scheduled jobs if they are running fine or not, right? So usually when we see time series data, right, in data science, when we encounter with time series data, so in time series context, there are certain models, right, like Holt Winters or ARIMA. But before going to that, let me give you a simpler example of what the time series data, what I mean by that kind of what it looks like, and what are the some of the terminologies associated with it. All right. So here I picked out another example. So this data is available in one of the Python packages. So I just plotted it and then took a screenshot and put it here. So on the y-axis, it shows a number of airline passengers, and x-axis is the time. So there is a time associated, right, with each of the observation. For example, this particular bar, right? So this shows around close to 200 passengers traveled in this particular month. So for each month, I have one data point over here, and there is data available for several months. And if I plot it, then visually I see two things happening. So one thing is over the years, this number is going up, right? The number of airline passengers is going up. So in time series context, this kind of pattern is called a trend, right? When there is a long-term upward or downward movement. So in this particular case, you see there is an upward movement, right? With time, it's increasing. So there is a trend in the data. And then another pattern that you see is there is some periodic event over here. For example, if you notice, so there is a peak occurring every year in the July month. So number of travelers in July is like the maximum in a given year, right? So every year, if you see July, there is a peak. And gradually it comes down and again increases and gradually it comes down. So this is like a periodic kind of movement, and the period for this is like 12 data points. So an event repeats after every 12 data points. For example, every July, so from this July to this July, there is a gap of 12 months, right? So that is what I mean by the period being 12 over here, and that is also known as a frequency, right, at which an event is repeating. So there are two elements to it, right? We have the trend and we have the seasonality, and a lot of models in the time series context. So they try to estimate, for example, Holt Winters, if you talk about. So it tries to estimate how much is the trend and what is the seasonality going on here, and then we can combine these two aspects and make forecasts for the time ahead over here, that uh, for the next year here, right, for which we don't have the observations available, what do we expect, like how many passengers would be here. So there are time series models available to do that. So again, coming back here, so we had this time series data, and our first thought was like, let's try if some time series models if I can use, and what kind of results uh, we get, what kind of accuracy we get. So so that same job, the first job that you saw in the previous slide, that data is plotted over here, right? If I go back, so I'm talking about this particular job. Okay, so on the left over here, if I plot it again, and this red line shows to the left of the red line I used as a training the model. So I used the whole twinter method, and then to the right of this red line is the forecast from the model, right? So here you can see that my training data looks like this. Visually, if I see there is some pattern that is repeating, right? So visually, it appears to me that there is seasonality, right? Although it doesn't qualify with strictly the definition of seasonality that is there in time series, right? But visually, initially it appears there seems to be seasonality. We don't have much of a trend going on, but there is some periodic event that is happening, and let's see if Holt Winter model can capture that. So here it's a daily data, one data point for each day, and if I assume that my seasonality is 30 days, like after every 30 days the pattern repeats. So with that kind of information, if I try to fit Holt Winter's method, I don't get very good results, right? And by the way, if you want to know more about how these methods work, like Holt Winter or ARIMA or many other models in time series, so there is a very good resource available online. There is a book called Forecasting Principles and Practice by Ron Heinemann, and if you Google it, it's available freely, so you can read about it and get more details about these methods. So then we started asking questions here, that why my forecast is not looking anything like what is there in the training data. And the reason we found was, although visually it looks like there is some seasonality, there is some periodic event going on, but the distance between these two peaks is not always fixed. Like in the airline data example, if I show you back here, right? So the difference, or the distance between these two peaks is always 12 months. So it's kind of happening at a fixed frequency, right? And that is when we call, the data has a seasonality. But in this particular case, right, when we started checking, so the distance between two corresponding peaks was not always 30 days as we thought. And when we started exploring further, we found that the distance between these two peaks could be 30 days plus or minus 2 days. So for example, in some cases, these two peaks could be 27 or 28 days apart, and in some cases, the two corresponding peaks would be maybe 32 or 33 days apart. And when we started investigating more and talking to some of the domain experts and the SMEs or subject matter experts for the mainframe, so what we found was all these events that are happening, so they are more related to the business days in a month, right? So what I mean by business days is like in any given month, if you remove the weekends and if you remove the designated holidays, then the days that are left over, that would be called business days. And these events that are occurring, those are related to some of the specific business days in a month. So this kind of discussion with the domain experts gave us some idea that if it's really related to business days, then instead of using Holt Winter kind of method, why don't we use a regression kind of method, right? And in that model, we can pass certain features which will capture that information, that what particular business day a given day is, and then see if that model performs better than this or not, right? So with that idea, we went ahead and created some features So features in the sense like in a supervised learning context, right? There are a bunch of X variables, and then you want to predict a Y variable as a function of the given X variables, right? So by features, I mean the X variables, right, which I want to pass as an input to my model, and the Y variable being the elapsed time the any given job would take, right? So if you see this snapshot here, I've put an example of January month where the days in the red are the weekends, and 2 other days are marked as holidays, and the days in blue are the leftover days that are the business days, right? And so in this particular month we see there are only 19 business days, and I have put a sequence like this is first business day, so BD1, BD2, and so on, right, till BD19. So we have 19 business days over here. So this was one of the features that we created to indicate which particular business day a given day is, along with a few other features such as indicators for a given day's weekday or a weekend, a given day's holiday or not. So we created certain features like these and a few more, and then passed it to a random forest model. And then we saw that with these features, the random forest model started performing very good, right? So with this given training data to the left of this red line, the training data, it was able to forecast, this is how the forecast would look like. And then this, kind of looks very similar to what we see in the training data. And when we validated, we saw a MAPE value. So MAPE is a metric, mean absolute percentage error, right? It's called the mean absolute percentage error, and it's a metric to see like how well your forecasting model is doing. So in this particular case, we observed MAPE like below 10%, right? Which is kind of really good, right, in terms of forecast. And visually also you can see, right, like this looks like a good forecast. It's able to replicate the patterns that is there in the training data, right? So with a random forest kind of model and using such features, this problem was solved. But as I said, there were more than 100,000 of jobs, and everywhere random forest model was not working. So we tried few other models, and eventually what we found was another model called simple exponential smoothing also works good in some other types of training data, right? So when the training data has some other types of patterns, so simple exponential model was working good. So what we were doing here is, like, say, if I have to forecast for next Monday, right? So there I would take how the job has performed, or what was the elapsed time for the given job on past several Mondays in the training data, and then take a weighted average by estimating the SES smoothing parameter, and taking a weighted average using the smoothing parameters to be able to forecast for the coming Monday. So this is another model that we built in along with the random forest model, right? And with these two models, we saw that across the variety of jobs that we had with their own patterns in the historical data, with these two models we started getting good accuracy, like kind of acceptable level of accuracy. Right. So this is how we implemented. So in the training data, in the model that we were planning to put into production, what we did was, for each job, what we do is divide it into training and test, and pass the training data to both of these models and see which model is doing better. So kind of a model selection step being involved here. Select which of these two models is performing better on a given data set, and select that model and use that to make the forecasts for the coming week or next 1 or 2 weeks, right? So with that, we were able to create forecasts or generate forecasts for next 2 weeks ahead within the acceptable level of accuracy, right? So when the time came, or before that, let me show you some of the results that we got. So for example, here, the first row represents the models, where we, or the kind of data where we got good forecast from random forest models. So you can see a comparison of actual versus predicted values. And we computed metrics such as MAPE or RMSE. We looked at such metrics to make sure that, these forecasts are within acceptable limits. So and visually also you can see like these are looking at good predictions, and in the bottom chart these are the forecasts coming out of some examples of forecasts coming out from the SES model, the simple exponential smoothing. And again, we looked at the some of the metrics to make sure that we have accuracy within acceptable limits. So with this being done, we felt happy that we are getting good level of accuracy, and now let's put the model into production. Now, when we were doing that, and as I also mentioned that there were hundreds of thousands of jobs. So while accuracy was good, another problem that we started facing was the model runtime. Because the sheer volume of the data set that we have, the number of jobs running into several thousands that we had, and for each job we were doing a model selection that which of these two models that I mentioned is performing better, and then use that model to generate the forecast. So to be able to generate forecasts for all those jobs, the model was running for close to 2 days, and that kind of model runtime was not acceptable. So model was taking too much time, and our goal was like we should be able to run model on a weekend, especially preferably on a Sunday. So let the model run on Sunday and generate forecasts for the week ahead. And we were not able to meet that criteria. So if I start running the model on Sunday, it would run whole day, and even it was taking Monday as well. So it was running for 2 days. So even though on accuracy front we were doing good, the model was taking too much time in order to generate the forecast for the entire population of jobs that we had, right? So then again we hit the bottleneck and started thinking, what shall we do? How to make the model runtime faster. So then we came up with this idea, like adding a third model called naive forecast. Okay, so in time series, if you search what is meant by naive forecast, what it means is, what it does is it looks at the training data and basically ignores most of the training data and just sees the last observed value, right? So to the left of this red line, we have this training data, and you see some patterns, some fluctuations happening, right? But this naive forecast ignores all of these past values and just captures this most recent observed value and copies that forward and says that will be my forecast. So it's like a flat forecast, a horizontal forecast that you see, right? For this particular job, again, y-axis here is in seconds. And in this particular case, it's close to maybe 0.4, 0.5 seconds. That is the forecast, right? So now on accuracy front, this naive forecast kind of model, you can see visually here that this is not looking very accurate. It's not capturing any of the patterns that is there in the training data, right? But the plus side is it runs very fast. There's no computation involved. It just copies the last value forward and says that this will be my forecast, right? So for next week, I saw that last observed value was maybe 0.4 second over here. So I will say next entire week, whenever this particular job would run, this would take maybe 0.4 seconds. So flat forecast. So accuracy wise, this will take a hit, but this is quite fast. So then we did this trade-off. And after discussions again with the domain experts and all, what we observed was we don't need accuracy for for that much accuracy, or we can sacrifice accuracy for jobs that are running very, very quickly. For example, again, if you see here, so this particular job can be called as a quick running job because it's finishing within few seconds. So for such jobs, which in the training data historically they have always finished in few seconds, although there is some fluctuations. But if they are never crossing 4 to 5 seconds, right? So I don't want to run a complicated model and try to generate accurate forecast, because for practical purposes that much of accuracy is not required, right? So then we added this third model also in the two models that we already had. We added this third model, and we put a threshold that for any job that we can call a quick running, and we put a threshold that if any job historically it has never crossed 30 seconds, so we will call them quick running jobs. And for such quick running jobs, we don't want to use complicated models. We will just use an eye forecast and use that as a forecast for the future. So after adding this third model, and then what we observed was 70% of our population of jobs that we had that fell into this naive forecast category, right? Where the 70% of the jobs were like quick running jobs, and for them, computing this naive forecast is like pretty quick. It can be done in few seconds, right? Like if because there's no computation involved over here, right? So after adding this third model, and then along with the random forest and SES models that we had to our model repertoire, we saw that our whole model runtime for generating forecast for my entire population, earlier it was 2 days, and then it came down to within 4 to 5 hours, right? So with that, with this solution, the model runtime also came within acceptable limits, and now it enabled us to be able to run this forecasting model within on a weekend, on a Sunday, and generate forecasts for the week ahead, right? And provide those forecasts to the IT operations team, right? So that was pretty much the use case that we did, and it went into production. And now this is my last slide, so I'm almost done here. So before I close, I would like to highlight what are the key considerations for any data science project, right? So whenever we start on data science project, first thing is we need to think, even before choosing which model to work with, right? Whether it should be random forest or SES or some sort of deep learning. The first question we need to ask is, what is the benefit of the model to the end user? For example, in this particular use case, the end user was the IT operations team, and our goal was, to be able to come up with a solution that will help them manage their operations in a better way, right? So what is the business benefit? What is the benefit to the end user? And then from that, we start and drill down and try to convert it into a data science problem and try to solve it. But this should always be the starting point. And the second would be, success criteria for the project. So when would I call, a project is successful, right? So at the model level, a successful project can be defined at an accuracy level. For example, let's say if I'm working on a classification problem, and it can vary from one context to another. In some contexts, 70% accuracy might be considered successful, and in some context, we may want 99% accuracy, and so on. So that is success criteria at the model level. But again, if you go a little higher and look into business side of things, then we can define the success criteria keeping the business also in mind. For example, the outage avoidance use case that I was talking about earlier, right? Reducing the unplanned downtime in my IT infrastructure. How can we do that? So from the business level, the success criteria could be before I implement any AI solution. So how many outages or incidents I was seeing in the IT infrastructure. And after this data science or AI project has been implemented, how much reduction I am seeing in the unplanned outages. So that would be, success criteria at a business level, right? So that is something we should define whenever we are getting into data science kind of project. Should be able to define like when we will call this project a success from model perspective as well as from the business perspective, right? And the third point, again, it's very important, is data exploration, which helps you understanding the data, right? How the data is, and this also helps you in asking the right questions. Right? When you start exploring data, then a lot of questions start coming to the mind, and then that leads you to interacting with the domain experts, right? So in this particular use case, I was talking about earlier in the forecasting problem, right? So we were having a lot of discussions with our clients, the domain experts, right? And after talking to them, that gave us a lot of ideas that what are the models we want to try, what are the features that we want to add into the model to increase the accuracy. So this is also important, like asking the right questions and interacting with the domain experts, right? And then the last point also that we learned was model accuracy alone is not sufficient. We also need to pay attention to model runtime. So in an enterprise kind of a setting, model runtime also matters a lot. And if I talk about, let's say, Kaggle sort of competitions, right, where people are building a lot of complicated models, and models really get complicated for every 0.1% increase in the accuracy. But if you talk about industry setting, right, in an enterprise, if I build a really complicated model, but if that is taking a lot of time to run, then it won't be feasible to implement such thing in production. So model accuracy and runtime, sometimes you might have to do a trade-off. Even if the accuracy reduces a bit, if the runtime is within acceptable limits, then only models are qualified to go into production. So with that being said, I think I'll stop here, and I'll take a pause, and maybe we can look into some comments, or if there are any questions. So let me go to the questions. Try to refresh here. Okay, so there's one question: what are the opportunities for placement of students after completing this degree? Okay, so I think the question you want to ask is, after completing this degree, you want to work as a data scientist or a data engineer or an ML engineer, or a ML researcher. So there are a lot of different roles, right? And while you're doing this course, you should also ask yourself that in which area you want to specialize. So you might find data engineers who are really skilled in several technologies and they know a little bit of data science as well. Or you might find data scientists who are really good in machine learning algorithms and all, but they know a little bit of ETL, exchange transform load sort of technologies, right? So before thinking about placements, I think we need to think like you want to get position yourself as a data scientist or a data engineer, or ML engineer or a researcher or stuff like that, and then probably I think we can go from there, right? And there are a lot of opportunities, right? I mean, LinkedIn, or there are job portals, or within IBM if you want to try. So there is an IBM career page. You can go through the open jobs that are there, that is matching with your profile, and apply over there. Okay, then let me see. So there are some questions related to this program. So what is the outcome of this program for a 2-year working professional? Okay. So, and in brackets, it's mentioned front-end developer. So if you are a front-end developer and trying to learn data science, right? So, now data science, it's a good area to be in, right? It's there's a lot of hype also around it, and every day, yeah, I mean, it's not just hype. There are a lot of opportunities also around it, right? So you'll see a lot of job opportunities, and not just data scientists. There are a lot of opportunities for data engineers. And as I was talking, data scientists or engineers don't work alone, right? So you need to have a little bit understanding about the domain, right? Interaction with domain experts as well. But having said that, after you're done with this course, I believe you will have some skills in data science, right? Some of the machine learning algorithms, and probably once you're done with this course, so these machine learning algorithms should not be a black box for you. For example, let's say if I talked about the random forest or simple exponential smoothing. So what are these machine learning algorithms do? And it's not just about using a Python package. Like these days, all these things are implemented in R or Python. It's very easy to use it. But if you really want to work as a data scientist, then you should not use it as a black box, would be my advice. You should really understand like what's going in the back end, how a random forest works, right? And so that's pretty important as well. Then there's a question. Kindly provide me just a second. I'll have to expand it a bit. So another question is, what kind of methods or tools are usually used to solve these type of problems? And how much depth in statistics is required? So to solve these kind of problems, right? So mainly today I talked about time series forecasting problem, right? And then I also talked about a random forest model, right? So to be a good data scientist, right? If I have to tell you, then yeah, knowledge of probability, statistics, linear algebra, optimization, little bit of multivariable calculus. So if you know these things, then you would be able to do your job pretty well, right? As I said earlier, if you're trying to work as a data scientist, then all these algorithms should not be you should not be using them as a black box. You should really be knowing like what is going inside and how all these methods are working. And in order to do that well, I think you should have a good understanding of probability, statistics, to some extent linear algebra, optimization, right? Those kind of things. Where IBM stands in data science projects like IoT, where data-driven interacting machines. So some of the examples, that I talked about today, right? The use cases that we talked about today. So those are falling under the IoT bucket, right? Because data is coming from the infrastructure, right? So it's not human-generated data or business application kind of data. Data is coming from devices that are connected to the internet. So all these use cases that I was trying to describe here, that is kind of coming under IoT umbrella itself. But there could be more use cases, definitely. Right. Can we get this presentation? So yeah, I think there would be a YouTube recording available. So I think you should be able to access that. And then what else we have? So how do we start looking for practical problems? And while we are doing this course, right? And there is another question of use cases in civil engineering. So suppose you are a in a civil engineering domain or any other domain, right? And in parallel, you're doing this course. So I would advise like try to see what is the kind of data that you deal with, right? So while you're doing this course, also keep in mind like you are coming from some domain, right? And maybe you have some expertise in that particular domain. So and both these skills are important. In addition to the data science, if you also bring in domain related skills, so both these skills are important in order to solve or do a project successfully, right? So while you're doing this course, I would say like whichever domain you come from, try to think like what are the data you deal with, and what are some of the use cases or the problems that you can solve by applying the kind of algorithms that you're going to learn in this course. So that's one. Maybe the next question, if I want to take. So what about higher studies that we can apply in the IT field, especially in AI? So for higher studies, there are many options, right? So for example, there's this course itself that you're doing. It's an online course. But if you want to, if you're thinking about some classroom course, right? So there are a lot of options available. For example, you can think of ISI Kolkata, right? It's that's a great institute, if you want to make a career into data science or statistics. So ISI Kolkata or some other name, maybe there is a CMI, Chennai Mathematical Institute. So, or there are many other institutes, right, where AI sort of AI related courses are coming up these days, right? So a lot of options available, and there are plenty of options available if you want to do it yourself. So if you don't want to enroll in a course and do it yourself, so a lot of platforms are available these days. A lot of books are available, like one example I showed you, right, on time series forecasting book that is available online. Many other books are available online. So one great book I would want to highlight here is Introduction to Statistical Learning, right? So if you Google for that book, Introduction to Statistical Learning, that book is by Trevor Hasty and Rob Tibshirani, and if you try to read through it, so that's a very good resource for learning some of these concepts. Then what are some of the challenges you faced in data science? So challenges, if I have to talk about myself, so I started learning data science. Like overall, I have 18 years of work experience, right? And out of 18 years, so initially I was working as a mechanical engineer, building CAD, CAM sort of applications. And my data science transition started, maybe around 7 to 8 years ago, when I decided that I want to come into this field and learn AI and data science and become a full-time, or work as a data scientist somewhere. So the challenges that I faced is like, how do you start, right? Where do you start learning? So I started searching about it, like what are some of the resources available, that which I can use to start learning, right? So then I came across platforms such as Coursera, Udacity, and some of the free online resources, some of the books that I mentioned. Then if you go to YouTube itself, if you search, a lot of great uh, uh, a lot of great material is available from one of world's best universities like Stanford and MIT. There are lectures available on linear algebra, on optimization, on natural language processing. It's available. Everything is available for free. All you need to have is devote some time, because it takes time to be able to learn these concepts. So if you're ready, if you're really interested into data science, so you should be able to devote some time. And there are plenty of resources available. They are available for free. All you need is time. And the other option is doing such courses as well, like the online course that you're doing. So that also saves some time, because such courses, or if you do it from some institute, so they present this material in a very structured way, right? So in my case, I was searching it myself, and I might have lost some time in order to finding these resources. But if you're doing it from some university or from some college, so they present you this information in a very structured format, so you don't have to do a lot of research, and you get a good head start in what are the things that you want to learn, right? So that was that. Then there's a question, is there an overlap with signal processing and ML? So a very good question. So yeah, signal processing is definitely applicable. If you have studied signal processing, then I would say you have an advantage, like especially when dealing with data such as time series, the kind of data that I was talking about earlier, or voice data, or even image analytics. So if you have some background in signal processing and want to learn some other machine learning techniques on top of that, so signal processing would be definitely a good start if you're aware of some of the signal processing techniques and the Fourier transforms and stuff like that. Can we apply data science in physics? Okay. So yeah, definitely you can. So data science and physics. So one application that comes to my mind is the Large Hadron Collider, right? Where the people are doing experiments and you don't visually see anything. So a lot of measurements, whenever an experiment is done, a lot of measurements is taken and data is generated in petabytes. And from this data, you have to observe and analyze this kind of data and then make inferences from there. So yeah, definitely there are experiments or opportunities in physics, where if you are measuring some data and trying to generate some inference out of that, so some of machine learning techniques can be useful from there. Okay, so we are out of time, but maybe I'll take this last question. So how to develop analytical thinking, which is very much needed working as a data scientist. How to develop analytical thinking? Okay, can you suggest any activities or habits that help? So I mean, yeah, again, it's a very good question. And for any data science project, so one thing is we need to be able to aware of all these algorithms in details, like how these things work. And then another thing would be like asking the right questions. So in order to do a project successfully, not just knowledge of machine learning is important, but also there's such as skills such as interacting with people, interacting with domain experts, asking the right questions, and that will come like what are the questions that you ask. So that will come when you start analyzing the data, doing some data exploration, and then wherever you don't understand the data correctly, so that is when you start asking questions that what is the piece that I'm missing, what is the piece that I don't understand correctly, and finding people who can help you understand and that. So I hope I answered your question. And maybe another thing would be do is to take some sample projects, right? So in your current domain, let's say if you don't have any available data science or readily available data science projects, that you can work on. So maybe you can look at platforms like Kaggle, right? So a lot of just do a Google search for Kaggle, and if you go there, so a lot of data science problems are posted, and they share data, right? And they also give you some starter code, like with this given data, what is the basic model that can be developed, and you can use that as starter code and try to improve the model. Right. So that would give you some practice. So over a period of time, I think you'll be able to build these skills related to analytics or asking the questions and stuff like that. And again, the another question is on. So if I have to take this question, so taking online courses, other than taking online courses, any suggestions for real hands-on concepts learned? So for hands-on exercises, again, I think I answered that in the earlier question itself. So there are platforms like Kaggle, right? So go there, see there are some competitions that are going on, some live competitions you might see, but that might be pretty advanced. But there are projects related to just for learning also, right? So just for learning as well, right? So you can look at those projects that are listed out in Kaggle, for example, image classification or text classification related problems that are there, and you will be able to download data from there and try some of the models that you want to try. So that would give you some ideas or some hands-on practice. So if it's not already there in your domain or in your current work, then platforms such as Kaggle, and there could be few others which host data science problems and then share data with you, right? And that could be a great resource to be able to get some hands-on experience. So I think with that being said, maybe we can close the session now.
Yes, sir, we can close the session.